When handling multi-arm or multi-robot configurations in a shared workspace, two main approaches are used for collision-free trajectory planning and execution. The synchronous approach treats simultaneously moving arms or robots as a single entity, while the asynchronous approach plans independent trajectories within the shared workspace, enabling individual arm autonomy. Asynchronous execution is more efficient when executing tasks of different durations and mixing coordinated and uncoordinated motions. In this work, we propose a method for asynchronous execution in MoveIt, which is the prominent planning and execution library in Robot Operating System. To support asynchronous execution, 3 changes were introduced. The collision detection strategies for multiple trajectories, central scheduler ensuring collision-free execution, and online collision detection. A central scheduler now allows the execution manager to handle multiple trajectories. When a new trajectory is added, it's checked for collisions against currently running trajectories. If no collision is expected, it is scheduled for execution, otherwise, it's placed in a backlog. Once the conflicting trajectory finishes, the new trajectory is re-evaluated for execution. The default collision checking library in MoveIt is Flexible Collision Library, which allows for discrete collision detection for a single robot state. At first, we tried evaluating collisions between a trajectory's discrete robot state at each timestamp and the interpolated state of another trajectory at the corresponding timestamp, but this led to undetected collisions, so we resorted to use a configurable parameter for the time step used to break trajectories into discrete steps. This allows to tune the trade-off between performance and operational safety. Our evaluation objectives include validating collision and deadlock avoidance, comparing asynchronous and synchronous approaches, and assessing proximity to the optimal result. Our experiments involve 2 7-degrees of Freedom Panda robot arms, operating in a shared workspace. Both arms begin with predefined home configurations, and are tasked with picking and placing cubes from a shared bin in color-ordered trays on their respective sides. We evaluated the following scenarios: 1. One arm, a theoretical optimum, assuming independent arms in independent workspaces. 2. Two arms synchronous movements, coordinated planning and execution. 3. Two arms asynchronous movements, our proposed approach. We assessed performance based on task completion time in the asynchronous execution compared to the 2 baseline cases. The pick-and-place operation encompasses 6 steps. To introduce task duration differences, we assume only blue cubes require inspection with parameterized duration delta of 6, 7.5 and 10 seconds. We kept the number of items to be picked small, 12 and 20 picks. The experimental data shows the average total execution time in seconds and standard deviation over 10 runs for the given pick-and-place operations. We cross the break-even point of T-sync and T-async between values of delta of 6 and 7.5 seconds for 12 picks. For longer pick sequences, example 20 picks, we have async consistently achieving lower total execution time than sync. Thank you.